Hello, good afternoon. Welcome to the series of metamaterial webinars. Today it's my pleasure to introduce Fernando Vasquez from the University of Utah in America. And Fernando is going to talk about ultrasound self-assembly of small particle pattern in a fluid.
Great, thank you, Myanmar, for the introduction and for the organizers for putting together this nice series of seminars and for giving me the opportunity to speak about this work. So first, let me acknowledge my collaborators in this. So this work is mainly done in collaborations with Bart Remakers, who is professor in mechanical engineering at the University of Utah. And I had the pleasure to work with a couple of his students, John Greenhall and Milo Prisby, who have graduated and are now at Los Alamos National Lab in New Mexico. And part of this work also has been done in collaboration with Elena Cherkaev, who is professor here at the math department. And last but not least is China Mok, who is my former PhD student. She just graduated, and it is thanks to her that you have this work, because she has done a lot of the mathematics that's behind this work. And now this is what I'll show you. And these are actually the slides from her defense with very minor modifications. So anyway, please stop me at any time, or if you have any questions, or I believe I should be able to see the chat somewhere. If somebody pops up at a message, hopefully I'll be able to see it. I don't know. Okay, so let's start with the motivation. So imagine that you had a reservoir, and this reservoir is filled with a polymer, some kind of glue that dries out, or that cures, that hardens with time, or maybe because you added something to it, or maybe because you let it out in the light. And imagine you take this liquid and you mix it with, say, carbon nanotubes, okay? So if you just do that, it's not going to make much of a difference to the material that you obtain afterwards. You know, the carbon nanotubes are going to be randomly oriented normally, and so it won't make that much of a difference. However, if you set up a standing acoustic wave by putting a couple of ultrasound transducers in the reservoir, so 2 parallel ultrasound transducers, then the expectation, at least, is that the carbon nanotubes will align in the direction parallel to the transducers, okay? And they were maybe clustered about the nodes of the wave. At least that's the expectation. And that's what has been observed also experimentally. My collaborator, Bart Makers, has done this experiment, and the resulting material that you get is actually reinforced to tensile strength compared to the material where the carbon nanotubes are randomly oriented. So this technique can be used to selectively reinforce a material if you want, if you can control waves in a certain way to achieve this. And why this happens is not clear, because the carbon nanotubes, they're not attached to each other. They're just next to each other. So it is thought that there's van der Waals forces or something like that linking to get the carbon nanotubes. All right. And why would this be interesting? Well, you could imagine putting that technique together with 3D printing. So in this particular type of 3D printing, what you have is a reservoir filled up with this pink goo, which is a polymer that can be cured using light. And what is done is, so this reservoir has a clear bottom, and one puts this slide projector underneath, and one projects the slice of what one wants to print on the bottom of the reservoir, okay? So putting light with a certain shape will harden up the polymer in just that shape. So you lower some platform very close and put it very close to the bottom of the reservoir, and so everything between the platform and the bottom will harden. And once it's hardened, you lift the platform a little bit, and then you print the next slice by projecting the shape of the next slice and so on. And so the idea of my collaborators was to actually add ultrasound transducers around this. And the objective of this is to print an object and at the same time modify its microstructure in some way, because you can imagine that instead of having carbon nanotubes, you could have other functional inclusions like maybe metal particles or something else in there that will have a drastically different properties than the matrix. All right. So what I'm going to do here is first I'm going to explore the limits of this approach. So we'll be working in a very idealized setting where I have essentially infinitely many transducers, and we will see that whatever particle patterns you can obtain will be limited by the diffraction limit. And then we'll go to two particular cases where you have finitely many transducers and which allow you to obtain either periodic materials, so materials with periodic inclusions, or where the inclusions form quasi-periodic patterns. Anyway, so this is the setup here. So that's the equation that the pressure would satisfy of a standing acoustic wave will satisfy. So it's just the Helmholtz equation where K is the wave number. And so that's satisfied inside this domain D. And on the boundary of the domain D, I have this Robin type boundary condition where the normal derivative of the pressure plus IK alpha times the pressure is equal to some function phi in here. So this is a non-homogeneous Robin type boundary condition. And what it expresses is the fact that, first of all, you may have different properties on the surface of the on the boundary of the domain, right? This domain here represents the reservoir where I'm putting the standing acoustic waves, right? So you may imagine that some portions of the reservoir boundary are simply the boundary of the reservoir, maybe plastic or something like that. And some other portions are the ultrasound transducers, which are, what is it, quartz crystals or something else, right? So the impedance of that material will change, and this alpha in here models that change. The other element in here is this phi. So the phi will be the corresponds to the excitation at the of the transducers to obtain a particular wave in there. One observation is that this is a linear equation. I'm not doing anything nonlinear here. Everything depends linearly on this excitation phi, and that's what we'll use. So if you wanted to look at the way in which the fluid interacts with the particles, you really have to go back to Euler's equation of motion in a fluid, because if you try to do this from simply the wave equation, you end up with something that won't work. What do I mean by that? Well, from Euler equations, what you do is you express the pressure as a constant pressure plus a small perturbation, which will solve the Helmholtz equation, right? So this epsilon times P1, where P1 solves the Helmholtz equation, and then plus some higher order terms in here. You do the same thing with the velocity. The only thing is that, well, the zeroth order term in epsilon of the velocity, you just assume that it's zero because you assume that the medium started in a quiet state. Nothing, the medium is not just moving around. You also expand so V1 also solves the wave equation in the traditional sense, let's say, and you can express also if there is a small scatterer in there, so that will be the particle in the fluid. You can express the total field as the incident field plus the scatter field. So what I meant from before, and I'm not putting that many details in here. If you want details, I have some slides at the end that I can show. But what I mean is that if you just focus on P1 and V1, so these are the things that solve the wave equation, and you calculate the net forces that this particle will be subject to, you get zero. You get zero because the forces, because these quantities are periodic, and so the forces will also be periodic in time. And so if you do the time average of the forces, you get zero. So in order to observe the effect that the waves have on the particle, you have to go further in this expansion. Okay, that's the only message in here. But once you go further in that expansion, you take the second order terms, you ignore the scattered field as well, and you ignore particle to particle scattering. So any multiple scattering is ignoring here. You can show that the force, net force, will be given by the negative of the gradient of some potential psi. Okay, so this is goes back to this formulation goes back to Gorkov, at least this particular derivation, and the potential is given as follows. So this psi, well, it's proportional to the volume of the particle. We're considering that the particle is spherical here. The potential will be different if the particle had another shape, by the way. This is simply the approximation that we're making here. But what is really important here is to remember that this potential is going to be given as a quadratic function of the incident pressure field and of the incident velocity field. Meaning I'm completely forgetting about scattered fields because I'm assuming that that scattered field is much smaller than the incident field. So there's no scattered field whatsoever in here. But what I have is the modulus square of the pressure and the modulus square of the velocity and averaged over a period of time. That's what these angle brackets mean. It means that I'm taking averages over a period to get the net forces. The other thing to notice is that you have these two non-dimensional quantities, F1 and F2, that kind of weight the two terms in here. So they depend on the following quantities. The first one, F1, depends on the relative compressibilities of the particles and of the fluid. So kappa naught is the compressibility of the fluid, and kappa P is the compressibility of the particle. And similarly, you have another quantity in here that's non-dimensional, and that depends on the mass densities of the particles and of the fluid, okay? So for example, if you had particles that are neutrally buoyant, meaning that the mass density is matched between the particle and the fluid, then these two quantities will be equal, and F2 is zero. So this term in here goes away, and you're only left with this term in here. And if on top of that, you assume that the particles are harder than the fluid, this is typically the case when you're having carbon nanotubes, let's say, in a fluid, the compressibility of the particle will be much smaller than that of the fluid, right? So this ratio in here will be close to zero, and F1 will be close to 1. And so the acoustic radiation potential in that particular case will simply be the time average of the modulus squared of the pressure. So if you go to the frequency domain, this will simply be and you assume time harmonic waves, this will simply be looking at the nodes of your solution to the Helmholtz equation at whatever operating frequency you're working at. Okay, so this is the model, and it has a lot of defects. I told you what the defects are, that it ignores multiple scattering, that it assumes that you have spherical shaped particles and that the particles are small, and so on. But it's still a model that agrees with what is observed experimentally fairly well. And this is the model that I'll be analyzing. So because it predicts where the particles go, right? Because if you look at this, if the force came from this potential, then if you look at the minimum, a minimum of that potential, then the negative gradient will point to that minimum, correct? So that means that all the forces will tend to go to that minimum point. So these are the traps where the particles will go to. So if we want to put a particle in a certain location, then we need to make sure that this acoustic radiation potential has a minimum at that location. So that would be how we make sure that particles stay in a certain location. Of course, that can be identified with the usual, second order sufficient optimality condition, meaning that if at this point the gradient of the potential is 0 and the Hessian is positive semi-definite, then I know I have, if I have a minimum, then I have that. If I want to ensure that I have a minimum, then I need this Hessian to be positive definite, right? And in the opposite case, where you have a point that is the maximum of the potential, then the particles will tend not to go in, to be in there, of course. Anyway, so that's the principle behind this. So first, let me ask this question here. This is a very general question. Let's say that you just want to draw something using particles. So you want to place particles on some closed curve. So is it possible to do in general something like that? I mean, what are the limits of this approach? Okay, even if you had infinitely many transducers, what can you do? So we did a study of this where we placed ourselves in the setting where we are just looking at the nodal sets of this Helmholtz equation solution, meaning the locations where the Helmholtz equation solution is equal to 0, okay? So we want to find a solution to the Helmholtz equation that is 0 at this particular, on this particular curve, okay? So you could do this, of course, if you had, you use the eigenfunctions of the Laplacian, right, on some domain, and you say that this U-shaped domain is your domain. But then you will have to adjust the operating frequency of the ultrasound transducers so that it matches that frequency, that eigenvalue of the Laplacian, right? So that's not very practical because when you get these ultrasound transducers, they have an operating frequency. They're usually, at least the ones that my colleagues use, they're usually narrow band, and so this is not a good idea. So instead, what the approach that we took in this particular study was to simply think of this curve as the level set of some function, okay? So that's another problem, but let's say that you can find a function that whose 0 level set is that shape that you want to reproduce. And then we ask the question, how well can we approximate this function now using solutions to the Helmholtz equation? Hoping that if we get a good approximation, then the level sets, the nodal sets, at least the 0 level set of this function will match the 0 level set of the solution to the Helmholtz equation. And so that's where the particles will go to, at least in that case where the particles are neutrally buoyant and they're harder than the surrounding fluid. Okay, so we did this approximation. We need to represent the solutions to the Helmholtz equation in some way. So we use these particular ansatz for the solutions, which are called Hairgloss wave functions. Okay, and what this is simply a superposition of plane waves. So what you have in here, this is a plane wave, right? Exponential of ix dotted with k. K is the wave vector. And because I'm assuming that I'm at a single operating frequency, then all these wave vectors will have the same length equal to k without bold in here, which is the wave number, right? And then this wave, these plane waves, they're weighted by something that depends on that direction. So you can think of this as defining a function on the sphere of radius k, this function being the g in here, and then that will determine a solution, a particular solution to the Helmholtz equation u of x by doing this integral here. There are, this is a way of representing waves in the far field. And it is known that you can approximate any solution to the Helmholtz equation arbitrarily well in say a compact set using this Hairgloss wave function. So this is a good choice for this. And we formulated the problem in two ways, and we got two very different answers. Okay, so in the first way we said, okay, you give me a function in a volume, let's say a ball of radius r, and I want you to I want to find the Hairgloss wave function that best approximates my function inside this ball. So the objective function is really comparing the L2 norm of two functions in a ball. And the problem with this is that your Hairgloss wave function, if you look at it, is really a two-dimensional quantity, right? Because it's really it really comes from integrating some density on the surface of the sphere. And using that two-dimensional quantity, you're trying to control a three-dimensional volume. So intuitively, there are more equations than unknowns in here. And so it's a kind of overdetermined problem, and you will not do a very good job at that. So this is we in this particular setting, we could compute explicitly what will be the solution to this problem, because it's some projection problem essentially. And we compared the level sets of this Hairgloss wave function that we obtained, that is supposedly the best approximation to some function, where the function was the characteristic function of a tetrahedron. So meaning that this kind of pyramid, right? We just put value of, say, +1 inside and -1 outside, and then we wanted to approximate this function as best as possible in some ball using these Hairgloss wave functions. And if you do that, so this is a slice of this. This is a slice of that pyramid. So you see this this triangle, and you see these level sets are completely useless for that purpose, because the particles again will go on these red curves and not at all on this black curves, which is where I want them to be. So we went back to the drawing board and we reformulated the problem as a problem of finding of simply enforcing the closeness on a plane. So if you still have you still work with Hairgloss wave functions, but you only want to approximate a function that's defined on a plane. So you want to look at the restriction of this Hairgloss wave function on a plane, and want to approximate, say, an L2 function in that plane. So in that case, we could also solve the problem explicitly. It turns out to be a projection problem, and it is related to taking the function on that plane and doing a band limiting operation, meaning that if it's an L2 function on the plane, then you can take its Fourier transform, and you can limit its spatial frequencies to only the spatial frequencies that are within a disk of radius k, where k is the wave number. So this is a way of, it's a low-pass filter in some sense. And this approximation by Hairgloss wave function is equivalent to doing this low-pass filtering, essentially. And that means that if you take a function like that I show you, that U function, and you approximate it and you show the level set of the approximation, you get a level set that is much closer to what you were, what you were planning. And the only caveat is that the level set will be it will look smoothed out because you filter out the high frequencies essentially, and you would expect for that this kind of radius of curvature is about one wavelength. So the features that you can resolve are of about one wavelength in this case, which is what you would expect. This kind of band limiting corresponds in some sense to ignoring all the evanescent waves. Okay, and it's related to so yeah, it's maybe I shouldn't say more about this. So this is what we did in this case, and just to show you that you cannot expect to have any kinds of patterns out there from this method. At least we don't think so. Okay, so let me jump to periodic arrangement. So this is a simpler setup where instead of having, so the setup that I talked before, maybe I should have said that earlier, it corresponded to infinitely many plane waves, right? So each plane wave, you can think of it, direction, you can think of it as an ultrasound transducer that's at infinity somehow, right? Very, very far away. So let's not think about infinitely many transducers anymore. Let's just think of a finite number of them and see what happens. So in this case, let's say we're in 2 dimensions and we have 4 transducers arranged in pairs, in parallel pairs. So I will keep saying, pairs of transducers. And whenever I say pairs of transducers, I really mean that the transducers are parallel to each other, okay? The reason is that I want to think of those transducers as generating 2 plane waves, right? If the normal to the transducer is K, as this K2 in here, then the field that can be generated by these transducers in here, these 2 transducers, can be written as a superposition of 2 plane waves. One will be exponential ik2 dotted with x, and the other one the same thing but with the minus sign there. And of course, you can weight these waves in any way you want, multiplying by some complex number alpha and beta. So if you, for these 4 transducers, you have this linear combination of plane waves where the sum here goes up to 2. And wave vectors have all the same norm, because we're talking about solutions to the Helmholtz equation. We're still working within the set of solutions to the Helmholtz equation. By the way, this is a subset of what we talked about before. If in this case in 2 dimensions, right? So that the Hairgloss wave functions will be integrating over a circle of radius k. And in this case, well, all I'm saying is that there are only 4 points on that circle where you're integrating. There's, well, 2 diametrical opposite points and then 2 other diametrical opposite points where all the density is. Okay. And then what I'm doing here is I'm also, well, it's just a linear combination of plane waves. And so these parameters that I have here, these complex numbers, I'm just putting them inside some vector u, just collecting them together. And you can think of this as the ultrasound transducer parameters that you're using for doing this. If you're doing experiments with this, you will feed, a certain periodic voltage to the transducers, and the alpha and the beta will model the amplitude and phases that you put in this sinusoidal wave. That's all it is. Of course, when I'm saying that, I'm ignoring any maybe electrical impedance between that driving current and the transducer, and any impedance between the transducer and the medium, and so on. But this is a reasonable model for in this case. Of course, this field also is a far field approximation. I'm assuming that the transducers are very, very far away, and if they're very far away, then this is the field that will get there. Great. So if you remember what we saw about the ARP, the acoustic radiation potential, it is given as a quadratic form in terms of the pressure and the gradient of the pressure, okay? So this quadratic form, I can write it in a slightly different way as follows. So where A is some matrix, that matrix will be this diagonal matrix where I have just this number A, which encodes whatever constants we define. If these are physical constants that define this term, which is quadratic in the pressure, and minus B times the identity of size D, where B is given by whatever constants were defined earlier. And then I'm even going to rewrite this a little bit more, because I noticed that the pressure and the gradient of the pressure depend linearly on this complex vector u, right? So if they depend linearly on this complex vector u, I can write the whole thing as a quadratic function of u, where the matrix that sandwiching between u star and u depends on x. Okay, and that's what we're going to use to analyze this problem, that the q of x is some matrix that we can construct, and that we can find its eigenvalues, eigenvectors explicitly, and so on. And so we can say everything about what that matrix is, and that allows us to conclude things about the acoustic radiation potential. Okay, so far so good. So that's the main observation here. Now, the second observation is that if your wave vectors form a basis in dimension d, so d can be here 2 or 3, then you can define these reciprocal vectors using this matrix C, which is just 2 pi times the inverse of the transpose of K, and K is the matrix where you put these wave vectors as columns. The reason that you do this is to show that the pressure field will be periodic in this case. So if you have 2 pairs of transducers in 2D, then you get a periodic field. If you have 3 pairs of transducers in 3D, then you have a periodic field as well. Why is it periodic? Because if you just plug in, if you look at what P of X plus this matrix C times any vector with integer entries, you will get back what the value of P of X at that location. So this is just expressing that this is periodic on a lattice with lattice vectors given by the columns of C. Okay. So this is just cooked up so that happens, right? Because if I have this relation, then indeed this Kj dotted with Cn will give you 2 pi or a integer multiple of 2 pi. Okay, so that's if the P is periodic, that also means that the acoustic radiation potential is periodic. And also it means that the particles that you're trying to place in your fluid, let's not lose track of what we want to do. Those particles will fall into periodic patterns, okay? All right, so now let's look at this of what this matrix looks like. I'm not putting details of what it is exactly. I'm just working off this property that can be proven for this matrix Q from the quadratic form that defines the acoustic radiation potential. So as you can see, if I look at what this matrix is at a point x naught plus epsilon, I can show that it is unitarily equivalent to the same matrix at another location x naught. It's unitarily equivalent, meaning that via change of basis that is orthogonal, change of basis vectors, you have the same thing. And what is the change of basis matrix is this diagonal matrix with complex exponentials on the diagonal. This is, of course, a unitary matrix because it's exponential of I times a positive definite matrix. No, I said positive definite. This is, well, anyway, this is not positive definite. But in any case, this matrix here is unitary. The D here that I put in here is the represents a diagonal matrix where I take this quantity and minus that quantity again, and I put that in the diagonal. It's just because of the structure of the problem, we put the transducer parameters that corresponds to plus K all together, and the ones that correspond to minus K right after. So that's why we have this kind of structure in here. And so once you realize this, you see that if I want to predict what the acoustic radiation potential will be at another location at x naught plus epsilon, then that corresponds to just taking my transducer parameters and multiplying them by this diagonal matrix with complex exponentials on it. So in other words, if you want to translate an acoustic radiation potential, all you need to do is adjust the phases of the transducer parameters. Keep the amplitudes the same, just adjust the phases. This is exactly what that does. And you have to adjust the phases in a certain way so that corresponds to a translation. That's one of the observations. The other observation is that you don't need to study this everywhere, this Q of X everywhere. You only need to study it at a point. So let's say if you study it at the origin, then you understand what happens everywhere. And that's what we did. So we studied this matrix at the origin, and we can find what are the eigenvalues and eigenvectors of this matrix. This is a small matrix, by the way. It's it has how large it is. It's one plus well, it's the U is the number of transducers that you have, right? So if in 2 dimensions, this matrix will be 4 by 4, and in 3 dimensions, this matrix will be 6 by 6, and it will be a Hermitian matrix that with eigenvalues that you can find. So the eigenvalues will be real, and the eigenvectors, you can choose them to have real entries in this case. And so what we were able to show is that if that eigenvector has any 0 entries, then then the level set corresponding of the acoustic radiation potential that correspond to this eigenvalue lambda will contain lines or planes. If, on the other hand, that eigenvector has no 0 entries, then the picture is a little bit more complicated. You have to take into account the symmetries of this eigenspace. By symmetries, I mean if you have an eigenvector inside that eigenspace, and if you flip the sign of one of the entries, and if that new vector with the flip sign stays inside the eigenspace, then that's one symmetry, you know. So we need to count this number of symmetries to determine either how many isolated points you will have within a unit cell, or whether you will get lines or planes of particles inside a unit cell. The other nice thing about this is that because all these matrices Q are unitarily equivalent everywhere, I can just calculate the eigenvalues once and for all. And by simply looking at the Rayleigh quotient here, so U is assumed to have norm 1, the acoustic radiation potential will always be between lambda min and lambda max, where that's the smallest eigenvalue and lambda max is the largest eigenvalue. So if I apply this result to the level sets corresponding to the smallest eigenvalue of Q naught, then I immediately know that level set corresponds to the global minima of the acoustic radiation potential, and that all my particles will cluster at those global minima, at least. This doesn't rule out any local minima, actually, but yeah. So it just predicts what the global minima will be. By the way, this number of points per unit cell may seem a little bit strange or suspicious. Whoops. So let me try to explain this in 1 dimension. And again, this is a solution to the Helmholtz equation in 1 dimension, right? That's 1 wavelength. And if I take the square of this, and I'm in the situation where the particles cluster about the nodes of the wave. So the nodes of the wave will be the places where this wave crosses the x-axis here, right? So if I take the square, then you see that you will have 2 particles per wave, per wavelength in this case, per unit cell. So if you were to do this in 1 dimension, we have 2 particles per wavelength because, you know, because of this little picture here. Anyway, so in 2 dimension, this is actually a plot of the acoustic radiation potential, and it's the locations that are within a certain percentage of the minimum of the acoustic radiation potential. So this will correspond to the traps where the particles will go. And we chose the orientations in certain ways to obtain hexagonal symmetry. And I believe this is the I forget, this is always not the cubic, the tetragonal symmetry, I believe, in 2 dimensions. And you see that in the unit cell in here, you have 2 points. So there's 1 point, the red point in here, and then the 4 points at the corner, which count for 1. In this case, you will have 4 points. You have 1 point for the middle, 1 point for the corners, plus 2 other points for the sides in here. And the coloring here is complete. It's just arbitrary in the sense that we're simply highlighting the particle traps that correspond to where we will place to the corners of the unit cell that we're taking, and everything else, every other trap we get is in red. So you see that you get more traps than you would sign for, or that you would expecting, because of you're essentially taking the square of some periodic quantity. Okay. You can, if you choose the transducer parameters in a particular way, you can also get lines like in this case, which is the case of a plane wave, or lines that cross like this in this unit cell. In 3 dimensions, you can get essentially lines or planes as well. But the more interesting question, I would say, is to study what kinds of periodic structures you can get in here. So you can go back to a result that says that there are only 5 types of Bravais lattices in 2 dimensions. So there's only 5 ways of tiling the plane periodically, essentially. So are all of these ways achievable using this technique? So can we create all possible crystals using this fabrication method? And the answer is no, because you are your wave vectors act as the reciprocal lattice vectors for the crystal that you're fabricating in some sense. And this reciprocal lattice vector have the constraint that they all have the same length. So not all these symmetries will be achievable. So even for yeah. So we focus only on the Bravais lattices that are achievable, in the sense that if imposing this constraint, one class collapses into another class, then we say, oh, that's not achievable, and we should just stick with the class that where there is at least one element that doesn't belong to the other class of Bravais lattices. Okay, so if you do that, that will, for example, rule out this case in here. I think this is rectangular, where A is different from B, because the fact that you're using your wave vectors are the reciprocal lattice vectors, it means that this A has to be equal to the B. So you fall into this tetragonal symmetry. So this symmetry is ruled out in the fabrication, and because it is, in some sense, becomes this one. So, excuse me, if you carry out the analysis, there are only 3 possible Bravais lattices: this orthorhombic center, the hexagonal, and tetragonal. In 3D, you do the same thing, and there's only 6 out of the 14 Bravais lattices that are possible, and these other ones, again, it's because of this restriction on the direction on the reciprocal lattice vectors. Okay, so what happens when you have more than 2 pairs of transducers or 3 pairs of transducers in 2D or 3D? Well, you get quasi-periodic particle arrangements. So the only thing that I made in here, I'm still considering a superposition of plane waves, still a Hairgloss wave function with point densities on the sphere or the circle, depending on whether I am in 3D or 2D. But I have more plane waves now, so more plane wave directions than I have dimensions. But I can still use the same model. Okay, and what's quasi-periodicity? So here is the definition that we use for this. So a function will be in dimension D will be quasi-periodic if it's not periodic, and you can find a function defined in a higher dimension n, such that f of x is equal to g of k transpose x. So k transpose is just some matrix in there that allows you to do that. In some sense, another way of putting this is a function is quasi-periodic if it is the restriction of a periodic function in higher dimensions to a hyperplane. That's the definition that we'll be using in here for quasi-periodicity. This has appeared or was in mathematics in the 70s, because people were interested in tiling the plane in ways with you know, a few tiles that never repeat. Penrose came with this nice tiling that is based off two kind of losanges or quadrilaterals that where you could obtain patterns that never repeat. So this was explained later by De Bruyn in the 80s with the cut and project method that I will explain this later, how this works, how these tiles are obtained. And it was observed, this rediscovered experimentally by Sheckman in the 80s as well, when he was analyzing this, some alloys of aluminum and iron, I believe. Magnesium, I'm not sure. Some metal alloys that exhibited this. So this is the diffraction pattern that you get from that crystal. Anyway, so let me just give an example to illustrate this quasi-periodicity definition. So, but starting with a periodic function, and just in 2 dimensions. So this is a very simple periodic function. It's just cosine of y1, y2. This is the y1, y2 plane, okay? And I'm simply going to restrict this function to this red line in here. That red line, y1 is equal to y2, is a corresponds to a subspace. And if I restrict that function, I get something that is periodic, right? Because if I set y1 is equal to 2y2, and x is the parameter that I'm using to go over this line, then of course the function that I get is periodic, because it's just what happens in here. You can see that will be periodic as well, because this line is crossing the lattice in here. Oops, it's crossing the lattice at another point. It crosses the lattice at the origin at another point in here, the point with coordinates 2, 1. So if it crosses at this point, it will also cross it at the one with coordinates 4, 2, etc. So you can see why this will be periodic graphically here, because this is the same thing as this, etc. Now, if you just change this, so the only thing I did between these 2 cases is I just adjusted the slope of this line by putting an irrational number linked to the golden ratio in here. So if you do that, then because you have an irrational slope, the line, although it intersects the lattice at the origin, it will not intersect the lattice again at any other point. Because if it did intersect it at a point, then this number phi will be rational, and we know that this number is irrational. Okay, so what's wrong about that? Well, there's nothing wrong about it. What it means is that you will get a function that looks almost like it's a periodic function, but it's not periodic really. I mean, if you were to plot this and zoom it out and so on, it will always look similar to this, but you'll never get exactly the same thing. Okay, so that's quasi-periodicity in 1 dimension. So if you are in this case where you have more dimensions and you have n pairs of transducers and you're working in n dimensions, then you can show that this quantity, which, because I mean in d-dimensional, I'll just write it as PD, is the restriction of another quantity, which is also superposition of plane waves, but in capital N dimensions, to some vector space, which is the range of this of K transpose. Okay, so this K transpose X for X in RD gives you a subspace, correct? And all I'm saying is that the pressure in D dimensions, if it's expressed in this way, can simply be written as another higher linear combination of n, well, 2n plane waves, but in n dimensions. And we know that this one is periodic from what we did before. So with this simple argument, we're saying that the pressure must be quasi-periodic. Okay. The other by a similar argument, there is, I mean, something there's a little bit more to it, but by a similar argument, you can show that sorry, this is, why is this? Okay, maybe I won't move my mouse. Probably, there you go. By the same argument, you can show that the acoustic radiation potential will be quasi-periodic. And what that means is that you can expect the particles that the particle positions using such a configuration to be placed in quasi-periodic patterns. Okay. All right. So this is a simulation of what happens if you had, for example, 4 pairs of transducers. So this will correspond to have an octagonal shaped reservoir, let's say, and where each side of the reservoir is an ultrasound transducer. That's the kind of pattern that you will have. With n is equal to 5, then you will get something that looks a lot like the Penrose tilings. So you have some kind of 5-fold symmetry. With n is equal to 6, you will get 12-fold symmetry. And these are pictures of the acoustic radiation potential. So you can expect the particles to go to the local minima. So this is a little bit more complicated than before, because before the global minima were basically all there was to it. And if we just look at the global minima, we could say where the particles will go. Here we need to look at local minima. So the question of finding where the particles will go, it's a little bit more complicated, but it's still similar to that. And we actually did some experiments with this. So my colleagues in mechanical engineering did this. So they created a small octagonal shaped reservoir. They put some fluid in there, water, and they put some particles. These are some carbon nanoparticles with, very precise sizes that they can get. So first, distribute the particles evenly, and then they set up a standing acoustic wave in there. So as you can see, this is an actual picture of the experiment. These are the ultrasound transducers. These are the wires that take the currents and drive these ultrasound transducers. And those carbon nanoparticles, they look blackish, so you can see them if you put a light behind this. And so these are these lines indeed into or assembles into these quasi-periodic patterns. Of course, this is not perfect, right? I mean, you see that around here, who knows what's going on? The reason is that I'm using a plane wave modeling here, which means it's far field. So I really can only expect this quasi-periodic pattern or getting something that's close to these quasi-periodic patterns that the theory predicts close to the center here. So maybe it's easier to look at it in this picture in here. So if these are my transducers, then the region in the plane that is the closest, that will give you something that is closer to a plane wave with this particular wave vector is it will be everything that belongs to this rectangle. At least in the high frequency regime, that's what you would obtain. So you take the intersection of all this and you get a smaller octagon with respect to good agreement between the plane wave model and the actual experiment. And we just simplify things and say, oh, it's just this circle in here with diameter equal to the side of the reservoir. We compare the simulations to the experiments with different transducer parameters, and we had to do some registration, right, between to make sure, because these experimental photos were taken with an iPhone, essentially with a cell phone camera. So the plane was not perfectly parallel to what you see to the plane of the reservoir. On top of that, there's also some parallax going on in here. What I mean by that, the reservoir, even if I'm using 2 dimensions here, thinking of this as 2 dimensions, the reservoir has a 3rd dimension in depth, and actually that's not negligible. It's about 1 centimeter of fluid inside the reservoir. So what you are seeing in here in this picture are actually columns of particles that go that span the whole depth of the reservoir. And so there is a little bit of parallax, meaning that they're a little bit inclined, right? Like when you're looking at a tube. Nevertheless, you can still register the approximate transformation that you need to take the photo to get the simulations. And we did this manually, so we just identified points that correspond in the two images. And we highlighted in here the location just by looking at the photograph as well, the location where the particles do cluster. That red circle in there is that circle where I can expect the model and the experiments to agree, let's say. And we compare the two in here, but it's probably better to blow up this so that you see what's going on. So as you can see, I put the simulated particle clusters in red. The observed experimental particle clusters are in blue. And as you can see, the two agree qualitatively, and agreement is better if you are closer to the center, because that's where my plane wave model is the most accurate. The areas in black are the overlap. So we measured the agreement by just computing this ratio here. So how the area in black divided by the area in black plus the blue area. And using this measure of agreement, you see that we get some reasonable agreement, and the agreement gets better as the if you make this, if you, instead of evaluating this on that circle of radius d, where d is the dimension of one of the transducers, one of the sides, you make this smaller, let's say half, a circle of diameter, half of the diameter that you had before, then you get better agreement than there. We were limited in these experiments by attenuation, right? Because if we could make a much larger, let's say, reservoir, but then we need to drive up the power of the ultrasound transducers really high, and that's much higher than whatever function generator that we're using can generate. So also, if you start putting too much energy in there, the liquid can actually boil. So this liquid was water, and it could boil because the ultrasound transducer just heat things up too much. Anyway, so let me go back to some math in here. So let me explain the cut and project method with, oh, I'm already over time. We'll try to wrap up, sorry. So I'll try to explain this cut and project method in two dimensions. So here is, again, basically the same example with a line that has a rational slope, and another one with an irrational slope. So the one with the rational slope hits the grid regularly, right, at many different points. This one only hits the grid or the lattice at the origin. And then what you do is you look at the only the cells that intersect the line, and you project the centers of those cells on the line. So you get these red crosses in here. And what that does is that partitions the line into tiles, if you want. So there's tiles that are orange and tiles that are blue, or short tiles. So in the case where you have a rational slope, then you get a periodic pattern of tiles, meaning you get short, long, long, short, long, long, short, and that repeats forever. If you are in the quasi-periodic case, then you get the tiles that will, in a pattern that never repeats. So here it's orange and then blue and then orange, blue, etc. But that pattern doesn't repeat. We could do the same thing in our case. So we could determine those. So let me blow up one. Superimpose the ARP with the tile that it would correspond to, and you see that there is a lot of agreement in what's going on. However, we cannot claim that, you know, this tile is exactly the same as this tile and as this tile, etc. But they look, there is a lot of correspondence between the two. And the reason that there is no perfect correspondence is that if you go back to this picture in here, I am plotting, I mean, the colors in there corresponded to something that happens only on this line, only on the subspace, and not and the tiles themselves, they come from something that is farther from that. It's just like the approximation on the cell. So that's why there's no real there is no perfect correlation between the patterns that you see and the tiles. But anyway, this is really cool because in some sense we're doing Penrose tiles using sound. So anyway. You can also change the parameters, so you get different locations of the particles if you change the the parameters A and B that drive the ARP. And you can use this translation equivalence property to translate the particles. But here I have more room to translate, right? Not only in space, but I can, because I have n dimensions, I can translate in all directions. So the directions of translation that are aligned with the plane that where I'm living, you know, let's say that we're in 2 dimensions, those will allow me to translate the patterns. And the directions that are orthogonal to that will allow me to adjust the patterns, maybe create new minima at certain locations. So to illustrate this, here's a quasi-periodic pattern, and we just put this circle in here to show how this feature gets moved. And we can tell you what the transducer parameters will be to translate this pattern. And in the same way, we can also look at what the directional derivative is in a certain direction. So this, if I move in a direction that is parallel to the plane, then I can get, for example, the derivative with respect to x1 of this pattern. Or if I am moving in the direction orthogonal to that plane, then I can create maybe minima at these locations, as these blue locations. That's what will happen. You can also rotate and reflect things. This is simply, you know, by rearranging when you're thinning the transducers, maybe reflecting it or translating it. So if it's one of these operations and it's compatible with where the transducers are located, then you can do these things. You can use this to create also media that are quasi-periodic only in one direction. So for example, I mean, periodic in one direction, quasi-periodic in the other 2 directions. So in this case, for example, I have a medium that is, if you look at it on each slice, x3 is equal to a constant, you get something that's quasi-periodic. But if you keep going, you will get the same thing. You get something that is pi periodic in here. You can do this in 3 dimensions as well. So you can get icosahedral symmetry. And this is harder to visualize, but you need 6 transducer pairs in this case. And if you just look at the, the volume occupied by these particles in this case, it just looks, you don't see any structure. But then if you align them in particular ways, you get either a 2-fold symmetry or a 10-fold symmetry. And this is characteristic of this icosahedral symmetry. So we just view this cloud of points in a particular way, and we get 2-fold symmetry. You get it in another way, and you get 10-fold symmetry. Anyway, so that's all I have to say. So thank you for your attention. Sorry for going over time. So I'm happy to answer any questions if you have any.
Sorry, Fernando. Can you hear me?
Yes, yes.
Okay. Thanks for the very nice talk. So now we have time for questions. So just please, just unmute yourself and ask any question that you like.